Hi, everyone. Welcome back to Let's Make a Better World. This is, I believe, my fourth video on a series on space travel. Today I'm going to talk about a very important topic, namely G-forces. And this is something that every astronaut has to worry about when they go on a space voyage. Because you don't want to have too many G's when you're going into space or when you're re-entering. So anyway, let's begin. I have to first tell you what G-forces are, what they mean. Let's just start by talking about Newton's second law of motion. You probably learned this if you were learning, basic physics. F equals ma. This is one of the most important equations in physics. Isaac Newton. This is Newton's second law. He discovered three laws of motion, which are basically the basis for all of classical mechanics. That and his theory of gravity. But what does this law say? It's a very simple law. F is force. So what this law says is if you have a body of mass m and you accelerate it with some acceleration a, which is measured in meters per second squared, it's just how fast its velocity is changing. Then if you apply force to it, that's how much it will accelerate. So the acceleration is really F over m. And the acceleration due to gravity is known as g. It's about 9.8 meters per second squared. So when you drop an object, it accelerates at 9.8 meters per second squared. And according to Newton's law, that's because of the gravitational force of the Earth acting on the object. That's just a special case of this law. But there's another important law in physics known as the equivalence principle. This was discovered by Albert Einstein much later, I think 1907. Newton came up with his laws in the late 17th century, 1660s, I believe. But Einstein came up with this principle, which is now called the equivalence principle, in 1907. When he discovered this principle, he said it was the happiest thought of his life. And here's how it works. So basically, imagine you're standing on Earth. Imagine you're just standing, in a room on Earth, and here's a picture on the bottom. You've got a ball that's falling. So say you're in your room and there's a ball on the ceiling that's falling down. Well, it's going to accelerate at 9.8 meters per second squared, like I just said, because of the Earth's gravity. But now, imagine another scenario. Look at the picture on top. Imagine that you're in a rocket in outer space where there's no gravity, but you're accelerating at 9.8 meters per second squared, and you're standing inside this rocket, this spaceship that has a rocket, engine on the bottom. And what are you going to see when this happens? Well, you'll see exactly the same thing. They don't show the astronaut inside. I think they should, but if you couldn't see outside, if there were no windows, you wouldn't be able to tell whether you were standing on Earth or if you were in a rocket ship accelerating at 9.8 meters per second squared. Everything would look exactly the same. The ball would look like it's falling at 9.8 meters per second squared. It's really staying in the same place. The rocket is accelerating the opposite direction. And you would still feel the same weight if you were standing on the floor right below the rocket engine. So that's a pretty powerful principle. So if you're, how many G? This is one G, by the way. So this rocket engine we call this one G. A G is just the acceleration due to gravity. So if the rocket is accelerating at 9.8 meters per second squared, we say that's one G because that's the acceleration due to gravity. That means if you were inside this rocket, you'd feel like you would on Earth. You'd feel one G. We always feel 1g when we're just sitting down or standing up when we're not accelerating. That's our normal g force that we experience. But we can experience more g's and we can experience g's in different directions. I mean, one way you can experience g force is if you're flying an airplane. And I've actually done this. I took flying lessons for 2 years. And there's 3 degrees of freedom of an aircraft. They're called roll, pitch, and yaw. Roll is when you rotate about the longitudinal axis. That's the axis passing through the axis of the plane, passing through the nose and the tail of the plane, if you like. And then there's also pitch, which is rotation about the lateral axis. That's how far up or down your nose is pointing, and that'll make you either ascend or descend. And then the third degree of freedom is what they call yaw. This is just when you rotate about the if you like the vertical axis, the axis passing through the center of the plane and going up and down. That'll make you turn, obviously. But if you do a yaw without what's called an uncoordinated turn, if you don't pitch the airplane and you just do a yaw, then you will feel a centripetal force, a centripetal acceleration. This is an acceleration due to rotation. So you can get different kinds of acceleration. This will also produce a g-force, by the way. You'll feel a g-force pushing you to the left or the right. It's still a g-force, and you probably all experience this. I mean, if you're on a merry-go-round, you feel a g-force, or maybe a better example would be if you're driving a car really fast around a bank turn, you feel your weight, pushing in the direction opposite of which you're turning. That's centrifugal force, and that's a g-force, but it's a g-force to the left or the right. There's three independent axes in which you can feel g-forces. So you can feel g-forces normally when we're not accelerating. If we're on Earth, we just feel a g-force straight down of 1g. But like I mentioned, if you're riding on a, if you're driving around a curve, you're going to feel g-forces due to centrifugal force, either to the left or the right, depending on which way you're turning. If you're accelerating, if you're in a car, like imagine you're a drag race and you're accelerating really fast, you're going to feel a really strong g-force pulling you back into your seat. And if you step on the brake, you're going to feel really strong g-force forward. And you better have your seatbelt on, otherwise you're going to crash into the front of the car, and maybe your head will go through the windshield. You wouldn't want that. So those are the different directions, and you can have a negative G. Another thing you can do, and I actually experienced when I was flying. If you do what's called I don't know what it's called, but if you pitch your nose way down, if you do like a stall, or if you pitch it down faster than gravity, which you can do, you'll experience a negative G. You'll actually feel your weight shifting upward, which is kind of scary. But anyway, so you can experience all these different directions of G forces and combinations of them. You can feel your weight in any direction and any magnitude depending on how much you're accelerating. So that's basically what G forces are and what causes them. And we have to be careful about G forces because the human body can only withstand, a limited G force. I mean, these graphs kind of show you how many G's, a typical person can withstand. And I think the red graph I think is the forward and backward. I mean the up and yeah. How is it? I don't remember. Yeah, up and down. That's what astronauts have to worry about. So astronauts really only have to worry about up and down G's because they're sitting in their seats and the rocket engine is below them. So they're going to feel their weight multiply as the rocket accelerates upward. And you can experience a lot of G's if it's for a very, very small period of time. This graph is sort of a semi-log graph. The vertical axis shows you G's, and I guess you can experience up to 35 G's for a very, very tiny period of time, like 0.03 seconds. We can withstand 35 G's for a 30th of a second. I guess if you just fell to the ground, you might instantaneously feel 35 G's and you won't die. Any more than that, you probably will. And then as the duration of the G forces increases, the maximum G's that you can withstand go down, and the limit on the right side of the graph is 30 seconds. So I guess most people can experience up to 10 G's for about 30 seconds. 10 G's is a lot. I mean, that's 10 times your normal weight. So if you weigh, say, 200 pounds, that means you would feel like you weigh a ton. You'd feel like you weigh 2,000 pounds. I wouldn't want to experience that. But that's what it is. So anyway, yeah. And now I just want to talk about the number of G's that the astronauts experienced on the different space missions we've been on. The first manned space missions for the Americans was the Mercury missions, and they used the Redstone rockets for this. These were kind of small rockets. I mean, they only had to launch one guy into space, so they didn't have to be that big. But one big disadvantage of the Mercury missions was they pulled a lot of G's. I mean, they went up to I think they went up to like 9 G's, which is about the maximum that they could tolerate, and that's why they had to do all this testing on these astronauts. They wanted to make sure that you sent up the astronauts who could withstand these huge G forces. Not everybody could, but I guess all the Mercury astronauts who went up were able to withstand these huge G forces. I wouldn't want to experience them, but they all did. But the good news was, as the missions progressed, the number of G forces that they experienced went down. I guess what happened was the reason why you have to have so many G's is because you have to have a rocket that's powerful enough thrust to get you into space. And I think the bigger the rocket is, the bigger the payload is launching, uh, the less G-force that it needs to get into outer space. I'm not sure exactly how that works, but if it's a bigger rocket, the thrust will be bigger, even though the G-force is smaller because the rocket's more massive. I don't know the details, but the Gemini, I think, only went up to about 7 Gs. So they cut the number of G's by 2. That's still a lot of G's. And you'll notice that there were 2 periods after the launch where the G forces went up. I guess it was right before separation. So when they were launching stage 1 and 2, went up to about 6 G's, and then when they discarded stage 2. I guess the G forces went to 0 for a second, and then they started growing again. Then it went up to about 7 Gs, and then they let go of stage 2, and then they were basically weightless once they were just in the capsule. And the same thing happened with Mercury, with the Redstone. And then the last one here is the Apollo. This had 3 stages. And the Apollo was much, much smoother. I mean, the Apollo only went up to about 4 Gs. And the Apollo astronauts only experienced 4 Gs right before the stage 1 separated, and then it wasn't even for very long. And then after stage 2, I think they only got up to about less than 2 Gs, and then stage 3 they only got to less than 1 G, and then they were weightless. So they didn't have to experience really huge G forces, which I guess must have been nice for them. And space shuttle is kind of similar to the Apollo missions. Space shuttle gets up to about 4 Gs. I was a little surprised by this. I always thought it only got up to about 3 Gs. I guess it gets up to about 3 Gs at first. It doesn't. I think there's like thrusters. There's these big booster. There's a big booster, and then that separates, and I think that's when that it goes down from 3 Gs. But then you have these other thrusters that are still firing until you're fast enough to go into orbit, and I guess that goes to about 4 Gs. So it looks like the space shuttle was similar in the number of G's to the Apollo, which surprises me a little bit. But I guess most people can stand 4 G's. I mean, that's 4 times your normal weight. I'm sure it's not that pleasant, but at least it won't kill you. Um, so anyway, that's G forces, and that is something we have to worry about when we go into outer space. So anyway, thank you for watching. Let's make a better world, and I'll see you guys next time. Bye.